So I mentioned it a bit before, so I'll now get you a few more details about this multi-grid aspect in WaveWatch, and that's actually running. So the idea is that you have different grids running together, exchanging energy. And instead of running W3 shell like we did yesterday, it's going to run with W3 multi. And the format of the input file is a bit different, but it has basically the same information. It only has a bit more information because it needs to be able to manage these different grids together. So I'll skip that. So yeah, multi-registered shell. What's very important is that each grid is identified by some extension. And so with W3 shell, we had everything was finishing with something.ww3, like moddef.w3, or even the forcing was win.w3. Now in W3 multi, it's going to be replaced by something dot, like for example, moddef grid 1. So for the grid number 1, it's going to be this. And this actually, we used the same kind of logic yesterday when we did the interpolation, the gint. So we were running the W3 gint to post-process the IRWAS mesh, going from the triangle mesh to the regular grid. And so the gint program also uses this logic. So it's only going to work with moddef W3. And so we have different grids. You need to move around the files to give them the right names. And so when you're doing this post-processing with a gint or the OUNP or OUNF, because these programs only work with files called something.w3, you need to link or move the files before you do the post-processing and after you do the post-processing. So that it makes this thing a bit more kludgy, but if you do it with scripts, it can be it can save you some typing time. And so these are a few examples. So basically, for one grid, you have the bathymetry. We'll see also this afternoon the obstructions, which is the mask for blocking for the small islands which are not resolved, and the model settings, which are defined in W3 grid. All that goes through W3 grid. You get the input file, and it generates the moddef.w3 file, which defines the model configuration. This is what's happening with already with just one grid. So if you have multiple grids, after you have done this step, W3 grid.imp, you move this file to the proper name you want to give, and these names will then be used by W3 multi. So if you have 3 grids, you can have 3 moddef files, which means you have to run W3 grid 3 times, or you make a script that calls W3 grid 3 times. And then you can also have grids specially for the different input fields. So if you have, say, you're running a global model, you want to use DFS winds or NWF winds, but then you have a zoom, and for that one you want to use the WRF winds or high resolution winds. So you would have different inputs, and you can use different inputs for different grids, or the same input for different grids. And all that will be managed by W3 multi. So you can have different forcings, and so my wind here is going to be called input, and I just make a grid, W3 grid for that input field on top of the real calculation grid. So for example, in our system, we're using NWF wind, so we have a W3 grid that we make for a grid which is the same size as our forcing grid. And then the interpolation from that grid to the different wave model grids will be done during the calculation. Yeah. You have to define. No. It may be inconsistent. That's that's nice. Yeah. Or you have to do something outside of WaveWatch. It will not do it for you. And then there's also to get the spectral output, the point output, which has a spectra. Because you have different grids, they may have different spectral resolution. Like maybe one grid has 24 direction, another one has 36. And you want to have all the points with the same resolution. You also define a grid for the point output with the same format. Of course, in that case, the spatial structure of the grid will not be used. It will only use the spectral resolution information, and then you move that to a moddef.spec, and that will be used to for the producing the spectra at this spectral resolution. So maybe some grids have more frequencies or more directions, this kind of stuff. And so when you do some post-processing, what you have is typically when you've been running the model, you have some out.grd file, but instead of W3 here, you may have grid1. So you need to move grid1 to out.grd.w3, and then you can run the post-processing. So here, for example, W3 grib to make some grib files, or W3 OUNF, as we did yesterday. And so you actually start from this file, you move it or link it to this one, then you call the W3 grib, and that will generate the grib file. And of course, so you need to move this one, you also need to move that one. So it needs both the moddef and the binary output file, okay? So the three types of grids that you can use in the model, and I just said that. So so there's grids for for the actual wave model grid, so the one we already use, the same kind of grid. You also have grid for the forcing, okay, and grids for the point output because of this possible different spectral resolution. Okay, yeah, several ways you can run W3 multi. You can actually also run W3 multi with just one grid, and this is what Lorenzo was telling me yesterday he's doing. And actually, the colleagues at NCEP are also doing it this way, because if you do that, you don't have to worry about shell and multi. You always use multi all the time, but sometimes you have only one grid, sometimes you have two grids. And the nice thing also with that is you can also have only one wind forcing, and you don't have to pre-process the wind. So you pre-process the wind only one at the same resolution as your wind field, like 1/8 of a degree for ECMWF or whatever you want. Then you have your binary file, and you can use this binary file for different wave model grids if you work with multi, because the interpolation will be done during the computation time. So that may save you a bit of disk space if you want. That's one possibility. It was a big problem before when people had to go through ASCII files and then pre-process. Now we're doing it with NetCF files. It doesn't take too much time to actually reprocess the wind again for 1 year or a couple of years. Just take like 10 minutes. So we're not doing it this way, but I know that at NCEP they do it that way. So they pre-process the wind once, and then you just store the binary file, and then you can run that with different grids. There's a bit of overhead, so maybe it may cost 2% more CPU time running with W3 multi compared to running with shell, but you can do it like that. And so you can have either all the forcing common for all the grids or for some grids. And you can also have each grid has its own forcing. And if you're using curvilinear grids or triangular grids, you actually have to have the forcing on these grids separately. So for example, we're doing simulation with the global ocean and then the Arctic. So we have to pre-process the wind twice, one for the Arctic and the other one for the global grid. In that case, you have to tell W3 multi that the format of the forcing will be native, so it's a native grid, not a different grid, and that will allow it to run. Otherwise, you cannot run with different types of grids, curvilinear and rectangular at the same time. And there are some examples in the reg tests, especially the MW36 reg test has some example of that. And yeah, so the easy solution is you look at in the reg test, you will find some multi-grid reg tests, and you can just start from these examples. All right, so typically also we have here 3 grids, so it means we can have 3 restart files, moddef also for the input, and so typically we're going to have some ice and wind here, and a moddef for the point. And so in that case, if you do that, it means that the ice and the wind will be on the same grid, right? Which will not be the case all the time. And then you have the input file W3 multi, INP. And so the program W3 multi will actually combine all this stuff together. Okay, so all these things for the restart and everything, and then all the moddefs, and it will run. It will produce, instead of producing a log.w3, you will get a log for each grid, and you also get a global log for the entire thing. So that's the global log that essentially tells you how the grids communicate together. And then the log for each grid looks very much like the log we looked at yesterday, and will just tell you, different time step what's going on. You get input and forcing and the output. The only thing that the log will not tell you, if you tell WFA multi to combine all the point output together from all the grids, so you don't have to, for example, you want output from one point, which is both in your global grid and your coastal grid, or you don't know where it is compared to the grids, but just, okay, just give me the finest resolution grid for that point. So you just tell that to WaveWatch, it will give you that. And so because of that, the output point will not show up in the log, but they will show up in the global log, not in the log of each grid. And then the result will also be some restart files for each grid. So you can redo your forecast for the next day starting from the restart. And of course, the output, the binary output now will be called outgrd and the name of the grid at the extension. And same thing for the points. So you could actually have technically different point output spectral resolution. So you get one outPNT point instead of outPNT.w3. What you need to tell WaveWatch is actually how these grids should interact. And essentially you have a hierarchy of grids. So there's like a parent grid and some sibling grids. So it's called by different ranks. So we have a global grid, which is our rank number 1. Then some grids at the high resolution, and you can actually have different ranks. So for example, you have the Northwest Europe, and then inside of that you could have a grid for Ireland, another grid for Portugal, and this kind of stuff. So they would be like rank number 1 for global, rank number 2 for Northwest Europe, and then Portugal and Ireland would both rank number 3. And WaveWatch then, if you tell it what is the rank of each grid, will be able to figure out how are they all linked together. So you can have grids that overlap and have the same rank. So you can have a Portuguese grid and a Spanish grid that have some overlap at the same rank. That works if you have rectangular grids. It doesn't work if you have a curvilinear grid for Portugal and a rectangular grid for Spain. Then what you would do is actually call the Portuguese grid rank number 3 and Spanish grid rank number 2, and then it will work. So the same rank grids only work for rectangular grids. And for each grid, you need to define the computation mask, and we will explain to you what that is. The input boundary points for each grid, and the time step information. And what you put in, the information put in multi is just the rank number, the source of input for each grid. Yeah, you tell it which wind and ice and whatever is used for that grid. You tell it if you want to have point output separately for that grid, or if you just unify all the point output for all the grids. And then you can also tell it that you want to use only one fraction of the CPUs. So for example, you have a cluster, you're going to use 64 processors, and you have a global grid and a regional grid. What you can do, and what we've been using until 2 years ago, we're still using, we're doing the global grid on the entire grid, and then we had the French grid and the let's say Spanish grid running one after the other, rank 2 grids on all 64 processors, but it's not very efficient because you have a lot of communication. What you can do is actually have the Spanish grid and the French grid run side by side. So one will take 32 processors, the other one will take 32 processors, and that would be much more efficient. And so if you have so one rank runs on all processors, and if you have grids of the same rank, they can run side by side. They don't have to run spread on all processors. That can save you a lot of CPU time. In our case, I think it was like a 502 in our multi-grid system. So it goes faster by having the grid of the same rank being allowed only one piece of the processors. And so in order to optimize that, you typically put in the same number of grid points, the wet points. If you have like one grid with 20,000 nodes, another one with 10,000 nodes which are wet, then you just put 2/3 of the nodes, computing nodes on one grid and 1/3 of the other grid. So you can, and there's actually some tools for monitoring the CPU usage for the different grids. And I'm not sure we'll see that second, but there's part of the WaveWatch package. There's some things for that. Yeah, for the nesting, you can also output some nest files if you want to rerun the one-way forcing after that, or not two-way forcing. We're not using that very often these days because it's all two-way nested, so why bother with nest files? But you can do that if you wanted. And the way you actually build your system, you typically start from building the big grids, the coarse regional or global grids, and then after that you will do the zooms into what we'll do with the grid gen tools. If you want to do it by hand, it's a bit tricky because you have to make sure that the input points for your fine grid are the same as the output point for the global grid, and this has been a nightmare with WaveWatch. The first time I was running nested grids in WaveWatch, I was pulling my hairs because it's really not simple to figure out which are the points. Because you have to know that the points from the global grid have to be wet in the fine grid, and if they're not, yeah. So people have tried that, they know what I mean. But the good thing that Arun Chal has made this nice MATLAB package called GridGen that does everything for you, and so you don't have to do it by hand, knowing if that point will be wet or if it's dry or not from one grid to another. And that's the way we use it. So you can do whatever time step you want for different grids, but what is recommended is that grids of equal rank would have the same global time step. That will make things a bit easier. And so you typically would like to have grids of equal rank having the same resolution. And you may want to use different time steps for different ranks, but you may want to make them integer multiples. So if your global grid has a time step of 1 hour, and you have a regional grid, instead of putting 2/3 of an hour, you may want to put half hour because it's going to have the same. It's going to do like 2 steps of the small grid to do the global step, not like one big step and another small step and stuff like that. So just try to use integer multiples for the global time steps of the different grids. And if you're working on a parallel file system, you also can worry a bit about the I/O access and making sure to use enough processors for writing to the disk. And you can assign some of the processors in your system for that. And I'm not sure I understand that very well. All right. And so there's these nice test cases that come in the reg tests called MLW3 test 1 all the way to 5, and also 6 will have the curvilinear grids in them. And what they do is, you typically have some lateral boundary conditions for 2D model, and you nest it. Yeah. Another one. There's one case which you have three grids with the same rank, which are essentially it's one way to do domain decomposition if you want, with two-way nesting. And so in the version 4.18, I think it's in the version which is public, there is also a tool to automatically take one big grid and cut it into small pieces to do this kind of domain decomposition. And yeah. Okay, so the data was showing. I showed you that before. So the data goes from the low resolution, high resolution, and you do some other thing after that. So the time space gets boundary data. So you have to. So here are the active boundary points, and then the other grid does something else. And I think I'll. And so that's some basic idea of how the averaging is done. So if you have your fine grid in green and your coarse grid in red, what's done is you just take all the cells that correspond to one grid point of the big coarse grid, and you average the energy together with a proper weighting with the area of these things. So what you average is a spectrum, of course, because that's the basic variable of the wave model. And so this is one example. We have one swell field here. And this is a case with which you have the outer grid, the inner grid, and so the region in gray here is actually not computed in the outer grid because WaveWatch knows that this stuff is already computed by the other grids. There's no way to waste. It's not necessary to waste your time computing that stuff, and so that's what happens. So this is a result with only one single grid. This is with one grid with the net one inside, and you can see that pass it through, and the energy gets carried back because it's actually going through the fine grid. So that works. And this is just to illustrate the different boundaries on that trend. Yeah. So that's one case with 3 grids. So I have 1 grid, a 2nd grid, and a 3rd grid. Okay, same resolution nested together, and it's all combined here. And here is using different schemes. Right, very funny. All right, another one. Okay, so it's going. So here it's going through different grids, and you have the swell here going through the land, and you can see a bit the. Here you have some funny effect that's due to the boundary as you go from 3rd order scheme to 1st order scheme at the boundary. Well, that's all right. And this is what they're doing at NCEP. That's typically a global 1 degree grid. Then you do another grid for all the Aleutian Islands at high resolution. And that's the result for the high resolution grid. And you combine it with the coarse resolution grid, and you get that. Oh, and that's, yeah. That's what you have in the regional grid. And when you combine the two, you get this. So you go from that to this. And you see the impact of actually resolving properly these islands in a better way that changes a bit what's happening on the other side. And it's merged well together. So this is typically the way we work with these multi-grid. So yeah.